So welcome all to my presentation. First I would like to introduce myself a bit more. I'm Vissers, I'm from the Netherlands. I have about 12 years of experience in HVAC design, construction and also support of commissioning, qualification and verification. I'm working at Kropman. Kropman is a Dutch-based company and we design and build clean rooms including all associated installations such as HVAC, black utilities and also clean utilities. Next to my work at Kropman, I'm an active member of VCCN, the Dutch Contamination Control Society, and I'm also participating in the ICCC 50 Young Professional program, as introduced already by Stephen. First of all, I would like to say thank you to ICCC because they gave me the opportunity to present here today. And I would like to introduce the 50 Young Professional program to you. We are, on behalf of the steering committee, I can say that we are still looking for more young professionals. And it's for everyone who's new in contamination control industry and seeking an area to grow, to learn and to give back to community. And what can you expect from ICCC? We're organizing webinars on a frequently basis. There is a mentorship program and you have the ability to attend ICCC meetings. And of course you can grow your international network. So if you're interested, please come to me after this presentation or visit the website of the ICCC where you can find an application form. Then to the agenda of my presentation. And I based the agenda of my presentation upon the key trend I observe in the world of clean rooms. What is that sustainability is getting more and more important in both design, construction, but also in the operation of clean rooms. And the new clean room standards, part 4, on design, and also part 16 on energy efficiency do fully support this. It was already mentioned a couple of times yesterday in the presentation of Mr. Ward and also in the presentation of Mr. Fargenson. And today I will focus on the design aspect. I have two topics. The first one is from air change rate based design towards source strength particle emission based design. And the second one is how can we reduce the source strength in our clean rooms. And we can do that by keeping equipment partially out of the clean room and also by keeping humans out of the critical area. And there we see more and more automated processes and also robotics. And I will show you some practical examples about source strength reduction. If we look at the design of clean rooms, you can distinguish two types of airflow concepts. Left one is the unidirectional airflow concept, which is based on the ventilation mechanism of displacement. And the other one is the non-unidirectional airflow concept, which is based on the principle of dilution. And in my today presentation, I will focus on the non-unidirectional airflow clean rooms. And the airflow rate is mainly calculated by multiplying the room volume times an air change rate. And as mentioned multiple times earlier in the earlier presentations, the air change rates are guidance values or rule of thumb values. They are not scientific and not contamination control specific at all. So it does not take into account the actual process in your clean room or the amount of operators or the clean room garment. It's just a rule of thumb value. Here I show you some typical guidance values we are used to in the Netherlands. For example, if I take a grade B clean room, ISO 7 in operation, we design it at 40 air changes per hour, and grade C, 20 air changes per hour. However, a clean room is not defined based on any air change rate. If we look at the definition of a clean room, it's primarily based on the concentration of particles in the air. So why still a lot of our clients write down the number of air changes and also consultancy companies down in the user requirement specifications. We as Kropman always say, please write down the ISO class or GP grade, and then we calculate for you how much air is required. And of course I understand that for decades this worked quite well when sustainability was not an issue. But I think now we have to use another approach. And the new ISO standard on design, construction and startup, part 4, gives a straightforward equation, which is quite easy to fill in, to calculate how much air is required based on the estimation of the particle emission in your clean room and the ventilation effectiveness. And we have one known value. The known value is the maximum particle concentration in your clean room according to the ISO class. But we have two known unknowns. That is the source strength and that is the ventilation effectiveness. What about source strength? We know from literature that people are the main source of contamination. And in literature we find also a lot of values already, but there is a huge variation in between those values. First of all, because the body box values you cannot compare exactly with the operational values we find in our clean rooms. And in one of the latest articles in Cleanroom Technology, Mr. Agricola from the Netherlands, he presented a table with average source strength values for different type of cleanroom garment, for 0.5 micron, 5 micron, and 50 micron. But he also stated in this article that the accuracy of those values is plus minus 50%. And in one of the latest webinars, he also mentioned that when the activity levels are much higher, those values can be up to 3 or even 4 times higher. So for us as designers, still difficult to design on. And what about the second known unknown, the ventilation efficiency? It depends on the airflow pattern throughout your clean room. So it's depending on the location of the supply and the return, but also on the type of diffuser. I think you all can imagine in this situation, if this is a cross-section of your clean room, that the ventilation efficiency in location 1 is much higher than in location 2. So we found guidance values between 0.7 and 1.3 in our projects, and in literature also, where 1 is perfect mixing, 0.7 is worse, but a good design value, and 1.3 is actually a really good value, and we found that in our clean rooms in the Netherlands where we measured it, meaning that the local air change rate is higher than the average air change rate in your clean room. And of course, CFD simulations can help to predict those values more accurate, but still CFD simulations also have their limitations, and the output is highly depending on the quality of the input. So the question remains, in my opinion, how do we get better values for the source strength and the ventilation effectiveness? And we, as designers, can be very happy or lucky with pharmaceutical industry because there's already a lot of data available. Especially when we talk about manufacturing of sterile medicinal products, an EMPQ study must be performed to determine the critical EM locations in your clean room. And during this EMPQ, the clean room is, there is a maximum occupation in your clean room. So the maximum amount of operators is in the clean room doing the process. So it's the worst case scenario. And then you are measuring the particle concentrations, but also the CFUs in the air, sedimentation on surfaces. And if we combine that with our operational qualification data, then you can calculate what was the actual source strength in your clean room. Because during operational qualification, you determine the airflows, but also the recovery times at different locations in your clean room. Based on this data, you can calculate what is the actual ventilation efficiency, and combining this with the EMPQ data gives you the source strength during the EMPQ. I will show you an example. Here you see the EMPQ results, 3-day measurements with, for a grade B clean room, ISO 7 in operation, initially designed at 40 air changes per hour. Clean room is fully occupied, 24 operators, and more than 20 measurement locations in the clean room. And what do we see is that the measured concentrations, especially when we look at the particles, are much lower than the class limit of grade B. And this is not the only clean room in the Netherlands where we observe this big gap between class limit and measured concentrations. for me, the first indication that we over-design our systems. For CFUs, it's a little bit different, but I will come back to that later. So what we did, we took this data, we took the peak value, the maximum counts for particles, for example, for 0.5 micron, and then you can calculate what was the actual source strength during the EMPQ. And we also know the ventilation efficiency from the recovery time measurements, and then you can calculate how much air was actually required in my clean room. And that's not 40 air changes per hour, but that's only 16 air changes per hour when we look at the source strength data, and that's based on max counts. Worst case scenario. So if you take the average values, then it's only 5 air changes per hour. So meaning the system is really over-designed. Later on, the same client asked us to build a new clean room in the same facility. Identical size, identical setup, identical number of 24 operators. And we decided to design it at 25 air changes and not at 16 due to internal heat loads expected and also because of recovery time requirements. And later on, the client decided to run it at GMPC and not at level B. So the main difference is gowning. I mean, in grade B, the face is fully covered, and in grade C, the face is not covered at all. And here I show you the results. EMPQ study, again, but I represent it not against grade C limits, but against grade B limits. And again, for the particles, a big gap between class limit and the measured concentrations in the worst case scenario. For CFUs, it's different. We see a lot of peaks, but I think that's more related to the level of gowning and level of cleaning in the clean room than relying on the air change rate. And after 1 year measurements, we saved almost, we saved 45% of the fan energy. And this brings me to the sub-conclusion on this part. So we have seen in the Netherlands already a lot of oversized systems which were initially designed based on air change rate. When you design based on the source strength, you have a reduction on energy consumption, but also a reduced size HVAC system, meaning the footprint of your facility is reduced. So you need less space in your technical areas. And of course, energy consumption can be improved more by smart controls. So usually we apply a setback mode, meaning during idle hours when there is no occupation in the clean room, you reduce the air change rate even more. And another option is adaptive or dynamic control. And probably next speaker is going to tell you more about, I'm not sure. But the key message is that if you design on source strength, you will get a reduced size system, but also reduced size components. And if you have an oversized system, you have oversized components. And if you're going to run at really low air changes due to smart controls, then your components are getting out of the selection range. So it's for that reason, I think it's also better to design based upon source strength instead of any air change rate. But now I'm talking about designing on particle emission in your clean room. But the first thing we should actually do in our designs is trying to minimize the particle emission. And in many projects, when we talk about equipment, we see that a lot of surfaces are fully exposed into the clean room. And those surfaces are difficult to clean and are a potential risk for contamination. So why not installing all technical components out of the clean room and keep only the areas used by the operators in the clean room? And the conceptual thinking is as follows. It's an example from EH where motor and gear are fully covered from the hygienic area. That's a good solution. However, if you have to go there for maintenance, you still have to enter the clean room area, or the hygienic area. And also the heat load of the components is still in the clean room area. So a better solution to my opinion, is to use full separation. So design all technical components in the technical area and design only the components which have to be in the clean area, design that on the other side of the clean room wall. So apply full separation. And I will give you some examples. This is at one of our clients. You're seeing an operator adding ingredients to a vessel, but the vessel is fully installed in a non-classified area. So it means that all technical cleaning challenges are outside the clean room. You can use normal construction of the system, do normal maintenance to all those components. And a big advantage, the heat load is also outside of your clean room. And locally, you have minimum contamination control while adding the ingredients or components. This is another example, also at one of our clients. It's a 2,000 liter formulation vessel, and only the top is in the grade C clean room, and the rest of the installation is downstairs. Again, most technical cleaning challenges outside of your clean room, normal construction of the system, and normal maintenance. And all with the objective to minimize the source strength in your clean room. And then the last example, it's one of our cleaning out of place installations. In a grade D area, only a docking station to connect your mobile vessel to. And the rest of the COP installation is fully in technical area, so you can do maintenance and do not have to enter the clean room. So for equipment, when I talk about equipment, in my opinion, designing empty is beautiful. Don't you think so? And then the most difficult ones, to reduce the source strength of the humans. We know, what I told you earlier, people are the main source of contamination. And of course we have our clean room clothes as a filter between the human body and the environment. And when a product is really vulnerable for smaller particles of CFUs, then we apply barrier technology to separate the operator from the critical product area. And this can be done by, for example, wraps or an isolator. This shows a picture of a passive open wraps with a grade A area and a grade B background. But such a wraps still requires human intervention. For example, for the assembly of pre-sterilized parts for different container sizes. And what we observe in the Netherlands in the pharmaceutical industry is that it's going from semi-automatic towards fully automatic, step by step. But that's the trend we are facing in the Netherlands. And the advantage of fully automatic system with robotics is that gloss and human intervention can be reduced or even fully eliminated. And you can also have systems which are flexible for multiple container types. So there is no need to pre-sterilize all change parts anymore. So although you have the energy consumption for the robotics, you can save energy for your autoclave, for your steam sterilizer. And you do not only see it in filling line applications, but also in ATMP facilities. A couple of years ago, it was only manual, doing the work in a biosafety cabinet. Nowadays, it's semi-automatic. And I heard that they are working on fully automated processes. And also in other industries, for example, semiconductor industry, we see more and more automated systems. So yeah, I think that's the trend, and it's also fully in line with what Annex 1 is telling us. And of course, there are some challenges to overcome. So about automation and robotics, I think human intervention can be reduced or eliminated. You have an increased flexibility, and of course, you can apply them in high-risk areas with containment issues. And the drawbacks is the initial investment, and also they require high qualified personnel for the setup. And another aspect, what was mentioned yesterday, is first air. is the robot arm not between the UDAV area and the product, impacting the first air, what is mentioned in Annex 1. And that brings me to my view on the future cleanroom. I think we will see in the coming years more and more barrier systems with robotics, keeping humans out of the critical area, keep equipment we can keep partially out of the cleanroom. And due to the closed barrier systems, the environment can be of a lower grade, meaning less air is required for the cleanroom, and we will see reduced size HVAC systems and HVAC systems which are controlled based on the real contamination challenge in the surrounding environment. This brings me to the takeaways. I think I've shown you that design based on source strength will reduce facility and HVAC size, and of course energy consumption, without compromising the cleanliness level. And EMPQ data will help us all to get better values for the source strength and ventilation efficiency. So I encourage you all to ask your clients to provide this data so that we as designers get better values for it. And to reduce source strength, keep equipment partially out of your clean room. And you can keep humans out by more and more automated processes and also robotics. And that was my presentation for today. So thank you for your attention.
Thank you, Derek. That was excellent. That was really good. And
thank you.
Some practical, in use kind of environments. So you've proven the kind of the theory of source strength. That's really good. Have we got any questions? Yep. It's keeping me fit, this is.
Can you envisage somewhere where you're going to the dynamic control, but rather than just being when personnel are not in the area, it being real-time feedback based on the particle counts and things you're getting, so literally up and down speed to get more air to take the contamination away in real time, where we're talking with the robotics and the like?
I'm sorry, we don't have implemented the dynamic control at the moment.
But can you envisage that being the future? So I think by 2025, there's a drive for most filling operations to be dark. You know, I think Novo Nordisk have got something. I know that there are several facilities that are being done. In that situation where there are far fewer sources, can you see this being dynamic as I've got real-time particle monitoring in there? I can therefore reduce until there's a 5% risk and increase based on real-time data.
Yeah, I think that's possible, but I'm not sure if there was already a particle explosion in your clean room, if you are quick enough with your HVAC system. But maybe I have to ask it to the next speaker, because they have implemented such a system already in a pharmaceutical clean room.
Brilliant, thank you.
After Gordon. Yeah.
You showed a slide with source strength from operators. I think it was credited to Course Agricola, one of your Dutch colleagues.
That's correct.
Is that published information?
That's published in Cleanroom Technology in March 2024.
Okay. Because it was one of the things I asked earlier on about, have we got more recent evidence than the old work of Bill White and the work of Lundquist and Reinmuller? So there's some...
This is data from Koos, and I know from Koos he received a lot of data from multiple clean rooms all over the world, and he combined it to those values.
Thank you.
Yeah, it'd be good to see that paper and read that paper in full, wouldn't it? Yeah. More?
So the top row there, it says cleanroom clothing, none. Was the person naked?
I have to look into detail, but I think it's normal clothes.
Street clothing,
yeah, street clothes.
That was my real question is, how do you account for, with the changing the the air volume in the room based upon particle concentrations. How do you account for the fact that the HEPA filters are rated for a certain flow and your flow is changing? So when you do the qualification of the room, the air velocity through the filters is different based upon your performance. So how do you do the leak testing? How do you compromise or adjust for that?
I mean, I would probably say that you would test that at the highest flow, because that would be typically the worst efficiency that you will get.
Right. But the filter efficiency would change with a different, I mean...
It would do, but it would potentially get better with lower flow, potentially.
Okay.
I mean, HEPA manufacturers are probably able to give us more information, but that would be my thoughts would be that typically the more air you put through a filter, the more likely you are to get leaks through it. So I would have, in that system, I would have set up and tested it a kind of maximum capacity flow for the system, and then if it backs down, you improve the efficiency.
But the specifications of the filter are different, right?
Yeah, absolutely.
Yeah, so
but I don't think you're going to find, with a HEPA filter, you're not going to find all of a sudden if you drop the flow by half, you're going to get hundreds and thousands of particles come through. It wouldn't happen.
But you just have to overcome it from a specification standpoint, I guess.
Yeah.
Okay. Thank you.
That's right. Any other questions? Yep.
I was just wondering, because we do like to give ourselves plenty of buffer in case things go wrong, and that's why we like, the air change rate thing. It gives us lots of space for issues. But I was just wondering, I think it becomes more pertinent as our facilities age, and because people don't want to invest in it. So if we're working sort of within finer limits, within finer specification, do we therefore have to upgrade more frequently? Or is that energy, because of the energy saving issues and things, will it actually prolong the length of our AHUs, HVAC systems and clean rooms? Or is it just not something we've considered?
I think the age of it's up to also other factors. I think the age of your HVAC system is more about the amount of hours running than on the air change rate itself. However, the fan efficiency, of course, you can improve by running at another air change rate. But that's energy efficiency.
I think also there might be a little bit of a, what's the word I'm looking for? A kind of mistruth about, old units don't perform as well. Well, if you think it's older, it's not going to perform as well, I need to have more buffer. It should perform exactly the same. You shouldn't be accepting the fact that in 10 years' time I'm only going to get 80% of the airflow through it. You'll need it all. So I think it's a little bit of a myth, maybe.
That's the message we try to share with our colleagues that we audit. Say, I know it meets specification, but it's dropped 50% compared to last time. So have you investigated that? And it's, they haven't until it fails. But I was just wondering, just because we like that nice, warm, fuzzy feeling, that's why we do sterility testing of things. It's the nice, warm fuzzies rather than actual management of risk.
Thank you. Cheers. Any more questions from anybody?
Thanks for the presentation, Derek. I have one question. You show us a great installation where you put the old tanks and everything into the non-classified area, and there will be additional risk because of the potential leakage through the ceiling, because they are all not static equipments. What will be the additional precautions that we can take in place to reduce this risk?
Let me.
Yes,
you mean
like
this installation or
this and the other one. Yeah. So in general, if you have this kind of installation, you always expose your grade C in this example to the outside ambient air, and this tank, even if it's an installed one, still there will be a leakage, potential leakage around. So what would be the...
You have the overpressure in your clean room.
Okay.
So the airflow is from the clean side towards the non-clean area. So the overpressure protects against incoming contamination.
Mm-hmm. Will that be enough to reduce the risk?
If you can maintain overpressure, there's no risk.
Mm-hmm.
But if not, then it's a potential.
That will be in trouble, huh?
Yeah.
Okay.
As long as you haven't It's about how you manage the whole system, isn't it?
Yeah, and also ISO 14644-3 has a new containment leak testing, where you can also verify that there is no leak exists, and you can start with testing on a monthly basis at the beginning to see that the design is confirmed, instead of finding particles coming out of the unclassified area. This could be one of the control parameter.
Okay.
But for sure there's a risk.
Thank you, Hashim.
You're welcome.
Thank you, Hashim. Any more questions from anyone? Excellent. Yeah, great. Some good questions there. Thank you, Derek.